Good afternoon, everybody. Welcome to Tea Time Talk. My name is Brenneis, and I'm a master's student in mechanical engineering under Patrick Polarski. And I'll be introducing to you today the handy hand, the humanoid, anthropometric, naturally dexterous, intelligent hand. And I say introducing, though this hand has been around for almost 2 years now, because it'll be making its debut into the academic community later this summer at the Myoelectric Control Symposium, and also as an open source release online fairly shortly. So if anybody wants to build their own, it will soon be available. So reinforcement learning, artificial intelligence, all that stuff applied to prostheses. So let's first take a look at how conventional prostheses are controlled. So typically, an amputee will have maybe 1 or 2 muscle sites that they can attach a myoelectric sensor to. And what they'll do is they'll contract either their biceps or triceps for an extend or retract of the robotic limb. And to select which joint that they're trying to control, be it the elbow, the wrist, or the hand functions, they'll select through a list of things that they can control. And they'll change their selection by co-contracting, so both at the same time. And selecting through a list like this is a really clunky and unintuitive way of controlling prosthesis, because all of a sudden you can't do simultaneous fluid motions anymore. And you have to think about which joint you're currently controlling. And especially for hand grasps. A lot of the multi-articulating hands that are available on the market will have many different hand grasps to choose from. So you can have a column grasp, pinch grasp, that sort of thing. And they'll have 14 or 20 different kinds of grasps to choose from, but again, they're in a list. And you have to go through the entire list to pick the one that you want. So it's not intuitive, and people will tend to use maybe 1 or 2 of their favorite grasps for everything. And what you end up having amputees do is using their intact body parts, their upper body and what's left of their arm, to do compensatory movements to make up for that motion that they can no longer get. And you can see that there's like this twisting in the trunk that is actually, over time, can be very damaging to these people, because they're straining the muscles in their upper body way more than you and I would be on a regular basis. So this is a pretty big problem for prosthesis users, and that's something that we're trying to solve with machine learning. So at this point, I'd like to introduce you to a friend of mine, Amelia. Amelia is a machine learner, and for the purposes of this presentation, she represents all of machine learners all across the world in a general sense. And so lately, Amelia has gotten really good at playing video games, guitar, and also very good at poker and stuff like that, even against real people. And that's all really exciting, and those are great advancements. But there's an interesting sort of problem that comes in when she tries to interact with the real world. Because the real world is wild, and the real world is sticky, and the real world is unpredictable. And it doesn't always follow this clear-cut set of rules that you can find in games and simulations. So this is an interesting problem that we face as artificial intelligence researchers, and something that we possibly could be looking at attacking by implementing machine learning in prosthesis control. So we have these 2 kind of separate problems. The prosthesis users are burdened by this control, and it's not something that they can cognitively keep track of. And at the same time, machine learners have difficulty with this wild and sticky world. So what we're trying to do is apply machine learning to prosthesis control so that we kind of solve both problems at the same time. And it gives us a good place to experiment with machine learning and see what happens when the rules do break. Because the person that's using this arm will not always want to do the same thing in the same context, for example. So hopefully, putting those 2 together, machine learners and prosthesis users alike will both become more readily able to interact with their world. So, if we're applying machine learning to prostheses, what kind of tools do we have to work with? The state-of-the-art in prosthetic hands is actually really quite exciting, because we have all of these cool multi-articulating hands that can move in pretty much all the same ways that the human hand can. But there are some drawbacks though. The Be Bionic and the Island don't have finger abduction, so that's this motion here. The MPL does, but of course it comes with a hefty price tag. And also a big problem is that there's not a lot of sensory information that can be gained from using these hands. Some of them have some sensors, for example the MPL has some sensors, but it's not something that we can easily use and get at as machine learners to try and learn stuff from. So we're running into this problem where we're trying to force our machine learners to see the world and make predictions about it and act in it, but we're not giving them the ability to see what they're interacting with, and that's a problem. So we needed a device to fill that gap. So I sat down with Patrick and we came up with some ideas of what sort of things might be necessary in a device like this. And of course, we wanted it to be sensorized, to take off that blindfold so that the hand can see the world that it's in. So we decided that force sensing of the fingertips, position sensing, so that's the position of the fingers in space, and we figured maybe visual information would provide a good context as a first kind of pass. So those are the three things that we decided we wanted to include. We also wanted the hand to be multi-articulating so that we could apply whatever we've learned in this platform to the advanced prosthetic limbs out there. And it would be really nice if this thing was inexpensive, so that research groups all across the world could get at this thing and do their own good research. So what we ended up coming up with was this handy hand, which has force sensors in the fingertips, position sensors in the knuckles, and a camera in the palm. And so what I'll be doing now is going over kind of the nuts and bolts of how it works, so that if any of you are interested in doing research with a tool like this, you have an idea of how it works and what sort of capabilities it has. So hopefully this works. Hooray. So on a high level sense, the way it works is you put in some kind of a control signal. And this can be any kind of an analog signal. In this case, we have potentiometers on this glove that just spin relative to where my finger's going. And it's sent out over Bluetooth to that Arduino. You could also use a joystick, myoelectric signals, anything that you can plug into an Arduino, like as an analog signal, can be used to control this thing. The Arduino then takes that information, figures out where it needs to go with the servos, tells the servos to go there, which affects the finger movement and draws them down. The sensors in the fingertips and the visual information, all that comes back to the Arduino. And then now that we have this sensory information in the Arduino, all we have to do is feed it to our machine learner. And let the machine learner learn about its environment and all that stuff, and then hopefully, after that simple problem is solved, we can just feed that back to the control. And then that takes a lot of the weight off the user as to like the different things that they have to go through thinking about the control. So as far as the nuts and bolts of how it works, the finger actuation scheme is fairly simple and common. The servos simply rotate and pull in this string that runs along the front of the finger, and that causes the fingers to curl up. And at each of the knuckles, we have a torsion spring, and that affects the fingers to come back once the servo rolls back and releases the tension on that string. Force is sensed by a force-sensitive resistor, which is embedded inside the fingertip. And the reason we embedded it is because then, as the hand's moving around and interacting with stuff, they don't move or get damaged, that sort of thing. So there's a column of plastic, 3D printed plastic, that moves in when there's a force normal to the finger that we're pushing here, and then pushes on this force-sensitive resistor embedded inside the finger. Position sensing of the knuckles is done by a rotary potentiometer. So the potentiometer body itself is fixed to this proximal end of the finger, and then through a D-shaped insert, this guy here, mates with this inside part here at the distal end, so that when that rolls down, the potentiometer spins, and then we can get that sensory information. For visual information, we just used a USB webcam. Just simply took it out of its case and plunked it right in the hand. And over the last term, we had a team of electrical engineering capstone students do some preliminary work with color and object tracking. So just to show that this can do this sort of object recognition sort of stuff. And they did that on a Raspberry Pi.
Wait, all the computation was on the Raspberry Pi?
Just basically what you saw in that video. It recognized a fluorescent color,
yeah,
and then where it was. and that's all that it did.
Okay.
I don't think they were running any machine learning stuff. So finger force. So I tightened up the servos as far as they could go and then measured the force at the fingertip here. So that would be the maximum force that one finger can output. And that was about 0.8 newtons. And then I measured the maximum grip force, that's in a column grasp, which is the standard way of measuring prosthetic grasp force. And that was about 4.2 newtons. Just as a reference, that's about the amount of force that it takes to hold a 500 milliliter water bottle. So it's a good enough amount of force for learning and laboratory type tasks, but not necessarily enough force as a take-home prosthesis. I also measured the finger speed, so full close from open to close as fast as it can go is a little bit less than half a second, so that's pretty darn quick. The capabilities for force sensing, I basically just put more and more weight on the end of the fingertip, the force sensitive resistor there, and measured to see whether it could actually discern the difference between these different levels of force. So on this y-axis here, this is just number of bits from 0 to 1023 of the readout of the FSR. So what this basically shows is that the FSR was able to discern that there was a force, anything over 20 grams it could sense. But there's too much deviation in the readouts to reliably determine between levels of force. So what you end up with is kind of a binary, is there force or is there not? I also measured the repeatability of the finger positioning. So that's full open and full close to see whether the fingers came back to the same positions at each time. And I measured that using the potentiometers in the knuckles. And so I was able to show that in the full open and full close at each position, they came to the exact same spot within 3.4 degrees of standard deviation across all of the knuckles that were measured. The exception being the D0, so that's the thumb rotation in this plane. And the reason for that exception was just that the way the potentiometer was installed didn't allow for accurate measurement of that particular rotation. So, if you wanted to build one of these yourself, it would take a little bit of time. It takes about 24 to 30 hours of build time for someone that has a pretty good idea of what they're doing. This was my build time. We had some capstone groups build their own hands, and I'm not sure how long it took them, but they did complain that it took a while. But the cost is really cheap compared to conventional myoelectric prostheses. If you wanted to get one of those multi-articulating hands, you're looking in the range of $20,000 to $50,000 depending which one you go to. So $800 is quite cheap by comparison. And if you wanted one just as a kinetic sculpture without any kind of sensor information, you're looking at closer to about $200. And the total weight of the hand was about 256 grams, so it's really light, especially also compared to conventional prostheses. So some future thoughts of what we might do. This control system here, we'd like to get that all kind of embedded inside the palm of the hand so that it's completely modular and you can just tack it onto the end of any limb you want and it can just do its own thing. So that's another thing that those capstone groups were working on, and we're still making slow progress on that. And I'd like to see more sensors, because the more things that you can see about the environment you're in, of course, the better predictions that you can make. So I'm considering putting in proximity sensors, current sensors, temperature sensors, and possibly like an accelerometer or inertial measurement point to see where the hand is in relation to gravity. Another thing that we need to work out is a little bit better understanding of how the heating in the hand is affecting things. Over like a number of long demos, some of the servos start to burn out, so we're doing a little bit of stuff on temperature control. But I'm hopefully working that out in the next little while before the open source release. So the real question here then is, what can we actually do with this in terms of machine learning and applied to control of prostheses? So one thing that I could see happening fairly easily is that your hand could see what object you're interacting with. And in knowing that, it could tell the arm what to do. So, for example, if you see a cup, you can make the automatic drinking motions. And instead of the person having to think about elbow, wrist, hand, all of that jazz. Another possible thing would be to inform hand grasp patterns. So if you were to see a pen, for example, you could automatically choose the pen grasp instead of having to select through that entire list. So really the take-home message, if you get nothing else from this, is that the hand-in-hand is a really nice tool to take off that blindfold and give your machine learner a pair of binoculars instead. Because the more that your machine learner can see its environment, the better it can do. So we want to give our machine learners the best opportunity to succeed that we can, because their success is our success. So that's about all I've got to say, so thank you very much for your attention. Are there any questions? Yeah.
So we were talking about how the hand can only really send force or no force as opposed to amount of force.
Right.
Can humans really tell? Because I was thinking about it. When I put my fingers on things, it's not really, ooh, that's 2 newtons.
Yeah. Yeah.
Force.
Yeah, you might not have an idea of like a number of it for sure, but if you are pressing really hard on your fingers, like to the point of pain, you'll notice the difference between just a light grade, right?
Oh, I suppose so.
Yeah.
Is that really necessary for controlling things though?
Perhaps not. So if you're holding onto something and you feel a force on your fingertip, you know that this finger is in contact with that object.
Yeah.
And that might be good enough information to do what you need to do. But if there was varying levels of force, you could say how hard the object is. If you're squeezing really hard and then there's a hard amount of force on that, then you know it's a hard object. But if there's not a lot of force, you're holding something squishy.
Okay.
Also,
Yeah.
if you're in charging of something delicate, that's what you said.
Yeah. If you're holding something delicate, then you want to know how much force you're applying.
Because you don't want to break.
You don't want to break.
Cool.
What kind of data files do you have?
I don't have any data files yet, so we've yet to actually run this on machine learning experiments. Once I figure out the temperature stuff in the hand so that it can run long enough for an experiment, then we'll have some good stuff.
How long is the limit right now?
It really depends on how the servos feel. Yeah, I've run for demos probably like 10 minutes max before I want to get them cooled down.
It's kind of tangential making question, but
Sure.
most of it's made of 3D printed plastic. What's the heat sink made out of how?
The heatsink is made of aluminum. And it's just a small aluminum sheet, and I just cut it out using a Dremel tool, which I don't recommend. So what it's doing is just taking the heat away from the servos and just kind of holding it in itself. So it's not actually dissipating that heat out into space so much as just giving you a little bit of extra time to play with.
So you need to get the hand fins.
Yeah, if I had
Yes.
cooling fins, that would be pretty
It's
cool.
Aquaman meets Wolverine.
Yeah. Yeah.
Maybe this is a bit more general, but all the hands that you showed and your hand as well, they seem to be made of like hard materials and like stiff motors and actuators. And it seems like all biological hands are soft, they have like this passive compliance thing. And is there, like, do you know of any efforts to try to replicate that? Because it seems like if you have soft actuators and soft materials, you can offload a lot of computation to just take the material properties of the hand itself to grasp things and so on.
Yeah.
Do you know of any work in that?
I have seen, I forget what the group was, but they had fingers made of like you said, a soft, pliable material. And it was the same kind of like string actuation system, but they had kind of embedded in that soft material was different kinds of sensors to see like how much it bent and like where it was bending and that sort of thing. So that was really cool to look into. I can't remember for the life of me where that was though.
I saw, I think, a pneumatic one at the last DARPA robotics competition, maybe?
Maybe?
I think.
I don't think I've seen that one.
Well, there's ones that fill with sand. They're kind of soft.
Yeah.
Like, yeah.
It's the ones that kind of inflate to
Yeah.
your grasp. It's like, I don't care what grip it is, it's all going to be the same at the end.
Or you already done that.
Yeah, so the way that mine and the other, the hard shelled ones, the way that they overcome this idea of compliance is that, so when I'm turning these servos, the finger will bend like where the force is, where it could bend down there. So it just kind of wraps around the object. And so by having the potentiometers in each of the knuckles, you could have an idea of kind of the shape of the object depending on which knuckles bend.
Who is your target audience for these things? Like, do you want them printed off by other research groups? Do you want to eventually make it so that it's like commercially viable? When I say commercially viable, I mean take home tool.
Yeah, so my vision for this is that labs and researchers could all print their own and then do their own research. Because I think that's the real benefit of something like this, is that it's got all that information that we need as researchers. But it doesn't have the durability that a real take-home prosthesis would have, and that's the drawback there. So, but I think commercial prostheses in the future should have this kind of sensory information because they're going to need it for if we're applying these kinds of machine learning techniques like online in take-home use. So I see the machine learning side of it being take-home, but not necessarily as physical prosthesis.
Interesting. Okay.
I remembered, regarding the soft robotics, I remember that I posted something recently about that on Amy. And so Harvard does some stuff that's in multi-material fluidic actuators. And so very much sounding like kind of what you were talking about. Soft robotics is essentially that field.
Any question?
You gonna try and run it on Arduino or Raspberry Pi?
The learning itself? I don't think we'll run learning on Arduino. It's not a whole lot.
Arduino and a computer.
Yeah.
Or
So,
Raspberry Pi.
I think what we've got now is a BeagleBone. So that we've got the Arduino to collect all the hand information stuff, and then we're sending it from the Arduino to the BeagleBone to do that sort of thing. That also works with the Bento.